Now we're continuing our this is a different approach, a little bit different approach from the book to the cross product and determinants. And I talked already about the determinant just in two dimensions, just two vectors in the plane, two dimensions, as measuring the oriented area of a parallelogram. And that's going to be something we're going to keep coming back to. It's a pretty basic geometric calculation. Now, what about volume in 3D? Okay, and right off the bat, we can guess, I think we mean oriented volume. If the natural thing that was coming out of the algebra was telling us to pay attention to an orientation, whether something was counterclockwise or clockwise, probably there's going to be an analog of that in 3 dimensions in terms of what we're going to do. And absolutely, that's absolutely true. We're going to come up with something that gives us oriented volume. Now, the oriented volume of what? Well, what's the natural analog of a parallelogram? It is a box. The official fancy name is a parallelepiped. Here's the base. It's made out of two vectors A and B, let's say. And then you take another vector C, this is supposed to be going out of that plane, and then you make a box out of that. And that's going to have some volume. And we're interested in whatever it would mean to be the oriented volume of this box. So we emulate what we were doing in 2 dimensions, and we first say, well, what is the data that even describes the box? 3 vectors in 3 dimensions. So let's say the vector A is A1, A2, A3. The vector B is B1, B2, B3. The vector C is C1, C2, C3. So I haven't done anything yet, but I've recorded the data in a natural way. And one very important thing is that it's still a square matrix. For it to have something that would define a meaningful area, a shape defining a meaningful area, in 2 dimensions it was a 2 by 2. Here it's 3 vectors in 3 dimensions. If I have 2 vectors in 3 dimensions, that doesn't have a volume. That's still back to area. Now that's of course what we're going to be actually doing for the cross product if you've looked at the book. But it's actually more complicated to start with that. This is really the more fundamental notion. The cross product is really derived from this. And most books don't tell you that, but it's a true fact. So we've got the natural thing is you've got 3 vectors in 3 dimensions, a square matrix of 9 numbers, and we'd like to know what calculation to perform on those to get the oriented volume. Well, once again, we'll get to a point where we can derive that from scratch later. It's a beautiful piece of mathematics, but we want more linear algebra before we want to attempt that. But what we will be able to do is we'll just sort of do some educated guessing and then you have to take on faith that I'm not leading you astray. So something like that. Okay. So again, let's look at this situation one more time. The answer should be proportional to the A's, proportional to the B's, and proportional to the C's. If I triple all of these simultaneously, I should triple the volume. If I triple all of these simultaneously, I should triple the volume. Same with the C's. Okay. What did we see in 2 dimensions? It was, in terms of the orientation thing, it was that if I flipped, if you look at the formula for the 2 by 2 case, remember what it was here. This guy was A1, B2 minus A2, B1. If I flipped the sign of A, that flipped the sign of the determinant, of the area. And that makes sense in terms of the orientation. If this is A and this is B, then that has a certain orientation. I'm going to denote that by a little curvy arrow pointing from A to B. If I flip A here, I've got a box of the same area, but it's oriented oppositely. So we'd probably expect that. That's not one of the things that you think we need necessarily, but we have to expect that from the formula. So minus sign in all of the A's, or all of the B's, or all of the C's should give a minus coming out. Okay. The other thing we expect is if let's call it the determinant. That's what we're going to call this volume operation. Let's just go ahead and say that. Let's think about the geometry of that simple case. That's when they're along the coordinate axes, and this is a rectangular parallelepiped or a rectangular box. Okay? And that should be A, B, C. Okay? And what else do we expect? We saw, oh yeah, when we have any two of these being the same, if C was equal to B, sorry, B was equal to A, sorry, then that should be 0. That's going to require minus signs, just like it did in the 2 by 2 case. Okay, so pretty hokey, but at least it gives us some means of determining whether I'm totally BSing you here. And here's this master formula. There's a few ways to write it down, but I'm going to purposely write it down in a way that lets us get to the cross product easier. I'm not going to write it down sort of in the most symmetric form. I'm going to give A little bit of a privileged position here. There's going to be, I'm just basically going to say, this is going to be a sum with signs, plus or minus signs, of products of A, B's, and C's. And pretty much already, based on what we've said it has to be true, it's not that hard to show that it has to be something like that. And so it's going to be A1 times, it turns out to be B2, C3 minus B3, C2. And then minus A2 times B1, C3 minus B3, C1. And we'll explain how to memorize this formula and understand it in just a sec. Or maybe I'll let the book do that. That's something the book does do. So this is a formula I can say, since you're reading the book, this is the formula you see in the book. Okay. Oh, that's a plus. That's pretty important. Okay. And hopefully, while I was talking, I didn't do something wrong. I think I tried. Okay. So let's see if that has the right kind of shape. First of all, it's got a bunch of pluses, minuses. It's got actually an equal number of pluses. Plus, and then minus, minus is plus, and then plus. As minuses. Minus, minus, minus. That's kind of nice and symmetric. It's 6 terms, if you just multiply it out. It's 6 terms, and each one has an A and a B and a C. Each one has a 1 and 2 and a 3. It's in fact all the different terms that have that property. So like A3, B2, C1. 1A, 1B, 1C, 1, 1, 1, 2, 1, 3. And so, for example, if you double A, well, there's a factor of A in everything. That'll double the whole answer. If you double B, you notice that B appears once in every term. Then that's going to double. Similarly, if you double C. So it's got that proportionality property. It's just slightly harder to see that if the B's were equal to the A's, it's going to die. But for example, here you get A1, A2, C3, and here you get minus A2, A1, C3. They all cancel on pairs. It's a pretty good thing to check for yourself, but it's not hard to check that that's going to happen. And that's really what the minus signs are doing for us. We really, really need it to have that property that if 2 of the rows are the same, it automatically dies. The only formulas where you can make things automatically die is where you have pluses and minuses canceling each other out. That's just the only way it works pretty much in math. That's the only way I can think of. Okay, so there's a formula, and the book talks about how you can think about this in terms of what you recognize is that these guys are 2 by 2 determinants of little matrices called minors. Okay, so I'll let the book handle that. If you haven't read it yet, now's the time, right now.